Hello. Our first unit is a general introduction to linear models. Um, in this section, we will discuss what is meant by a linear equation, what is meant by a linear model or a linear system. We'll discuss mathematical models more generally, and discuss how we formulate a mathematical model for a problem given, for example, a description of the problem in plain English. Um, we'll begin to recognize models of a number of common problem classes relevant to linear algebra, um, and begin to sort of notice that finding solutions, if they even exist, is often a non-trivial problem. This is really setting up the foundations for the study of linear algebra, and in particular, applied linear algebra. So let's begin with a little bit of a discussion about what is linear algebra and why should you or anybody else care. Uh, Most of us study math for one reason. It helps us solve problems that have a mathematical basis, um, often in a so-called real world um, application field. Mathematical models are absolutely central to problems in every branch of the sciences and engineering, in most of the social sciences, and even in a growing number of areas of the arts. One very common theme in mathematical models, regardless of the field of study we're applying them to, is that they're multidimensional. That is, they involve many different variables. Um, the real world is complicated. Models that try to address problems in the real world are equally complicated. Um, There are two key classes in a typical undergraduate curriculum that teach the foundational concepts, the language, the tools necessary to work with multivariable mathematical models. And these are linear algebra and what is typically called calculus 3, multivariable calculus. Of course, this is part of linear algebra. Um, Linear algebra in particular plays a central role in applications across a wide number of disciplines. Um, it is central to a number of important methods in statistics and data analysis, including regression and principal component analysis, um, linear programming, which is very commonly used application in industrial engineering and operations research, is grounded in linear algebra. Um, we use linear algebra throughout mechanical engineering and physics, um, electronic engineering, chemical engineering, biological engineering, and so on. Machine learning has many algorithms which are founded in the language and methods of linear algebra, um, and even sort of other computational science problems such as natural language processing, image processing, computer graphics, and so on, really can't be done without linear algebra. Um, it's not a stretch to say it is difficult, if not impossible, to do realistic math on real world problems without understanding linear algebra. Why is this? Well, linear algebra really provides a few different things. Um, One is simply an extension to the language of math. We'll be discussing in the early parts of this course uh, ways of talking about systems, mathematical systems, in a very, very simplified way, using concepts of matrices and vectors and so on, which uh, tremendously simplifies how we deal with, how we write down systems of many equations in many unknowns. In addition to an extension of the language of math, Linear algebra provides a set of tools, numerical methods, computational methods, and analytical methods that allow entire classes of problems to be solved in straightforward and robust ways. Linear algebra specifically provides a framework for dealing with linear mathematical models. We'll be defining what we really mean by that in a moment. But is also central to how many nonlinear models are solved. A very common way of solving nonlinear problems is by making approximations where we can treat them as linear in some regime and thus use the tools of linear algebra to solve nonlinear problems. So let's begin with a few definitions. What is a mathematical model? Mathematical models are going to be central to how our motivation for discussing really all of the methods we discuss in this class. So what is it? Well, a mathematical model really is simply a mathematical formulation of a so-called real-world problem. And it might be an actual application, an actual problem trying to be solved, or a somewhat contrived problem that we set up in a class, for example, but a mathematical representation, a mathematical formulation of a problem that might not seem on its surface as a math problem is what we mean by a mathematical model. Very often, these take the form of one or more equations that describe the problem, but there are other forms of mathematical models as well. And one of the important things to note is that classes of related problems can be described with a common type of model. Related problems often can be framed with related models, and then the tools that can be used for solving that in one model of the class can often be applied to other models of the same class. There are diverse number of methods of solving or using mathematical models. These vary based on both what class of model we're dealing with, what type of model we're dealing with, as well as the exact question being asked. The same model might need to be queried with different methods depending on nuances in exactly what is being asked. And we'll see some of that as we move through this course. Just as a sort of reiteration, mathematical modeling more generally is central to a very diverse number of fields. Climate modeling and prediction, epidemiology, that is disease modeling in public health sort of scenarios, as is particularly relevant these days with COVID-19. Computational pharmacology, vehicle design, neuroscience, large-scale data analysis, risk assessment, economics, and so on. None of these fields would be complete or anything close to what it is today without mathematical model. So that's a mathematical model. Linear algebra in particular is the study of linear models. What do we mean by that? Well, at its simplest level, a linear model is one in which all of the equations contain only linear terms. A linear term is one that has a general form of a times x, where a is some constant, perhaps a number or perhaps a symbolic constant, and x is a variable. Some examples of linear terms include 3x, 2y, bt, where b is a constant and t is a variable, 105 times z, 4ac times x, where 4 times ac is a constant, a and c are constants, and x is a variable. Nonlinear terms are anything that doesn't adopt that form. Sine x, x squared, x times y, x times the natural logarithm of x, e to the negative x. These are not of the general form constant times variable, therefore they are nonlinear. One thing that we noted on the last slide was the use of symbolic constants, A, B, C, as well as symbols for variables. I'd like to spend a moment here to sort of clarify how these differ and why we need to treat them differently. A variable is a symbolic representation of a number or a value that can take on different values within the context of a mathematical model. Sometimes there's a single value that we're trying to find, a correct value that's the solution, but we can plug in different values and it doesn't change the meaning of the model. That we can change the value of a variable and the underlying model doesn't change its meaning or its structure. A constant, on the other hand, is a value that remains fixed within the context of a single mathematical model. Sometimes we represent these simply by numbers, but in many cases it's more convenient to represent those constants as symbols. Sometimes it's just because the number they represent is hard to write down, things like pi or e. Whereas in other cases, we might use a symbolic constant because we may not know what the value is. We might be writing down a general model to describe the progression of a disease through a population, for example. And there are properties of the illness, properties of the disease that we don't know yet. We know that there should be some number to stick there, but we haven't figured out what that number is yet. We put in a symbol to represent that constant, kind of as a placeholder or as a way that we can work with the model generally before we know exactly what that number is. Importantly, though, changing that constant would change something important about the model, would change an important part of the model. It wouldn't be the same system, the same real-world problem we were representing anymore if we were to change it. I understand this may be a little bit confusing to some of you. Hopefully, as we work through various kinds of problems, the difference will become more apparent with practice. A brief note on conventions. Very commonly, variables are represented by letters towards the end of the alphabet. X, Y, Z, often T if the variable happens to be time, and in some other instances. Whereas letters towards the beginning of the alphabet are commonly used for constants, A, B, C, and so on. This isn't followed by everybody. It isn't followed everywhere. We will maintain this in the class unless otherwise specified, and it is a fairly general convention that you will see in most reading. So in an expression like b times t, in the context of the class, and in most contexts, if you are not told otherwise, it is reasonable to assume that b is a symbolic constant. It's a symbol that represents a number that doesn't change, whereas t is a variable. Similarly, for a cx, the most reasonable assumption might be that a and c are constants, and x is a variable. All right. So with that brief aside, let's extend our discussion of linearity and linear models. We discussed what a linear term is. It's a term that has the general form of a constant times a variable. A linear equation is, quite simply, an equation that only has linear terms in it. The general form of a linear equation is some constant times some variable plus some constant times some variable plus any number of constant times variable plus constant times variable and so on, equals perhaps some constant. Some examples of a linear equation are y equals 2x, constant of 1 times y, constant of 2 times x. There are no other terms, no nonlinear terms. Z equals ax minus by, assuming a and b are constants and x, y, and z are variables. These are linear. X plus y equals 5, all linear terms, a linear equation. 2x1 plus x2 plus x3 equals 7, a linear equation. Quite often in problems with multiple variables, especially with more than 2 or 3 variables, you will see variables represented with a common symbol, often x, and a subscript to denote which variable. So x1, x2, x3, used instead of x, y, and z, for example. The reason for this is simply that this type of structure of a subscript of a number allows us to write any number of variables we wish without running out of letters, whereas if we were trying to choose unique symbols, unique letters for each variable, we're constrained. In problems of only 2 or 3 variables, however, it is very common to use x, y, and z, or other variable names in some contexts as well. These are all linear equations. Perhaps the best way to demonstrate what a linear equation is to show you some things that are not linear. Y equals x squared. X squared is not a linear term, so this is not a linear equation. Z equals sine of x plus y. Sine breaks the linearity, so nonlinear. 2x plus xy plus 3y equals 7. X times y is a nonlinear term. It's a product of 2 variables, so this is nonlinear. If any term in an equation is nonlinear, the equation is nonlinear. Okay, we've discussed linear terms, linear equations. We are now going to move on to systems of equation. A system of equations is simply a set of equations that use the same variables. And when we say that they use the same variables, it's not just that we use the same symbols for the variables, but that the variables have the same meaning and must take on the same value in each equation in the system. Right? variables represent some kind of value within a model. The systems, the equations in a system all use those same variables to mean the same thing. Um, a linear system of equations is, once again, simply a system where every equation is linear, which means every term in every equation is linear. Some examples of linear systems of equations are written here. Two equation system with two variables. A three equation system with three variables, x, y, and z. A two variable equation with symbolic constants, a, b, c, and d, and two variables, x1 and x2. As with breaking linearity in an equation, if any term is nonlinear, the equation is nonlinear. If any equation in a system is nonlinear, the system is nonlinear. What this means is that if there is a single term anywhere in the system of equations that is a nonlinear term, it is no longer a linear system of equations. Now that we've sort of explained what a linear system of equations is, we can get to really what do we mean by a linear model. A linear model is a mathematical model described by a linear system of equations. So fundamentally, when we're talking about linear models, we're talking about mathematical models where all of the terms we work with are this linear form, a constant times a variable. All right. That's been very abstract, defining things in terms of what the equation looks like. It can really help understand, help an understanding of what a linear system is, what solutions mean, and even why we use the term linear to describe these by thinking about the geometry of these. We'll be discussing this at multiple points throughout the semester. This is just sort of a brief introduction to the geometry of these systems to start your brain thinking in these directions, or to give you a way of visualizing perhaps what some of these systems looks like. So let's start with the general form of a linear equation in 2D. 2 dimensions means 2 variables. A constant times the first variable plus a constant times the second variable equals some other constant. There's nothing really else we can do in 2 dimensions and still be linear. We only have 2 variables, and so a linear equation, a linear term, either has a constant times one variable, or a constant times the other variable, or just a constant. And so this is the most general form. If A2 isn't 0, we can rearrange this by subtracting A1, X1 from both sides and then dividing by A2. That's why we need A2 not equal 0. And that would give us an equation of this form. X2 equals negative A1 over A2 X1 plus B over A2. Again, A2 can't be 0 with this little rearrangement. It can be in a general linear equation. Doing this lets us see something about this general form. If instead of using x2 and x1, we used y and x, what this would look like is y equals some constant times x plus some other constant. This is of the general form y equals mx plus b, where m and b are constants, which is the equation for a straight line. The slope is m, the y-intercept is b. if a general linear equation in 2 dimensions is a straight line, then a system of linear equations in 2 dimensions is a set of lines, and a set of straight lines in a 2-dimensional plane. Solutions to the system, that is, variables, values of the variable that can be placed into both equations to make them true at the same time, are points where the lines intersect. Just as an example to visualize this, a system of 2 lines in 3D is given here, 2x minus 3y equals 3 and x minus 4y equals negative 8. Each of these can be rearranged into the standard form of y equals mx plus b. And when we do this, it makes it easy to plot. This first equation would have a slope of 2/3 and a y-intercept of -1. That's this blue line shown here, intercept of -1. The second equation rearranged gives a slope of 1/4 and an intercept of 2. That's this red line, a more shallow slope and an intercept of 2. These 2 lines intersect in exactly one place right here that looks somewhere between 5 and 10 in x and somewhere close to 4 in y. We could also walk through and try to solve this equation analytically. We'll discuss ways to do this. Oops, sorry about that. Essentially what we do here is we see these 2 equations both have y equals something. An analytical way to solve these is to set both of these equations equal to each other, since they both have to equal y. That gives 2/3 x minus 1 equals 1/4 x plus 2. Rearranging the x's on one side and the constants on the other gives 5/12 x equals 3, or x equals 36/5. Then plugging that value of x into either of these equations. Second one is pretty easy. So plugging 36/5 into 1/4 x plus 2 gives us 19/5. So 36/5, or 7.2, and 19/5 over 3.8 is where that point is. A geometrical understanding or a geometrical interpretation of what it means to have a system of 2 equations and what the solution means. In 3 dimensions, with 3 variables, the general form of a linear equation is something like this. X will constant times the first variable plus constant times the second plus constant times the third equals a constant. This is a general equation of the form ax plus by plus cz equals d, which you may or may not recognize as the equation for a plane. A plane actually described by a so-called normal vector of a, b, and c. If you don't recognize that form, it's not a problem. Take my word for it. A system of equations in 3D then, or a system of linear equations in 3D, is then a set of planes. Once again, solutions to the system, that is, places where the same variables satisfy all of the equations, correspond to points where planes intersect. And we can visualize this with a system of 2 planes in 3 dimensions. Here are 2 planes, 3 variables, x, y, and z. The first equation I believe corresponds to this plane that is sort of yellow in the top and shaded towards light blue moving down. Just as when we represent a line on a two-dimensional plot, we may only show a portion of the line, but the implication is that if we expanded the axes, that line would continue forever. The same thing is true for a plane. This plane is truncated because of the range of values that we're constraining x, y to be, but we should imagine that this flat surface actually extends infinitely in all dimensions. The second equation is this sort of darker plane that slopes in the other in an opposing direction. And these two planes intersect actually along a line highlighted here in red. This is a visual representation of what the solution of this system would be. Any point on this line is on both of this planes is a solution to the system. And we can analytically work around with this in a number of ways. One way is to try to remove variables. I look at this and I say, if I add these two equations together, I'll make z disappear. So adding the two equations would give me 2x, x plus x, minus 3y over 2, negative y minus y over 2, equals 6, 4 plus 2. This lets us write x as a function of y. If instead of adding these two equations we subtracted them, we'd make x disappear. X minus x is 0. Negative y minus y over 2 is negative y over 2. Z minus negative z is 2z, and 4 minus 2 is 2. We can rearrange this to give z as a function of y. There's not really much else we can do with this system, but we have managed to sort of simplify this. We have managed to write x in terms of y and z in terms of y, but nothing we do with this system will be able to give us an individual number for y, because actually all the solutions lie on a line. There's many, many different ways to satisfy this equation. One way we can write a solution to this is in a so-called parametric form. We say y can be anything, so let's call that, let's replace y with a value t that can be any number. And then write x is 3t4 over 4 plus 3. Y is just t, and z is t over 4 plus 1. We'll be discussing these sort of ways of representing systems and solutions to systems again further down the road. This is just to give you kind of a preview of the sort of thing that we might be looking at. All right. So as a very sort of brief extension that might help you understand sort of or help a little bit with intuition of larger dimensionality problems, I just want to very briefly sort of discuss how we might extend this. A linear equation in 2 dimensions is a line. A line is a one-dimensional object, and it's flat. There's no curve to it. A linear equation in 3 dimensions is a plane. A plane is a 2-dimensional object. It's also flat. There's no curvature to it anywhere. We might then extend this idea, and it can be proven that this is in fact what happens when we extend this, but at this point we're just going to sort of take the intuitive jump towards this result. A linear equation in any number of variables represents a flat geometric object, plane, a line, and so on, with a dimension exactly one less than the parent space. In 2 dimensions, it's a flat one-dimensional object. In 3 dimensions, it's a flat two-dimensional object. The general term we use for this kind of object is a hyperplane in dimensions greater than 2. And just as in 2 dimensions, solutions are the intersection of lines, solutions to a system in 3 dimensions are the intersections of planes, we can extend these ideas. Solutions to systems of higher dimensionality linear equations are points where all of the hyperplanes intersect. We'll discuss this later on. I do want to emphasize visualizing things in 2D is often easy. Visualizing things in 3D can be helpful for a lot of people, but also presents challenges. When we move into higher dimensions, visualization really isn't possible, and there isn't a perfect sort of match between what we see in 2 and 3 dimensions and what's going on in higher dimensions, but we get a feel for how things might be working in the smaller dimensionality spaces and trust that the same ideas extend in higher dimensions. All right. I'm going to stop our discussion of these kind of more theoretical aspects for now. And in the next recorded session, we'll work through some simple problems associated with the ideas that we discussed here. Thank you.